All right, let's talk about complex numbers. So, you may have learned about complex numbers in Algebra 1. And so we're talking about imaginary numbers. That's what we're talking about here. We're talking about the i's, the square root of negative ones, all that kind of stuff. I'm going to give you more details. Don't worry, don't stress. I am going to give you all the things in this video. But before we do that, I wanted to tie in and give you, kind of reveal behind the curtain and show and let you know how this is going to tie in back to quadratic functions, and we'll see this later. So we talked in a couple videos ago, a couple lessons ago, about the fact that there are different types of solutions when it comes to a quadratic. So where this is going to tie in, and I'm not going to spend like any time on this, but where this is going to tie in is going to tie in when we have something that has no solution. Okay, and that's where it's going to tie in. I'm just going to give you that and just kind of give you that worm in the back of your head to kind of get in there and lock in, and so you can understand things better later. So, like I said, let's put some details in here. So we're talking about I. What is I in math, right? In this context. So what I is the square root of -1. If this is your first kind of learning about this, then it's worth noting, because it could be true. It's worth noting that up until this point, possibly you have been taught that you can't have a negative inside of a square root, which is kind of true. You can't have a real number inside of a real number and have a negative inside the square root, but you can have an imaginary number, a complex number, as we're going to call it later. Okay, so that is the definition of I, and that's kind of what we're going to be learning in some examples and practicing some examples dealing with that fact. So before we kind of get into some more meaty examples, let's kind of think about the properties of I, because there are some interesting things. So I is the square root of -1. So that means that I squared would be the square root of -1 times the square root of -1. Well, square and square root, what do? They cancel out. So that means, let me rewrite this one more way. It's the square root of -1. Let me kind of erase this top one. I think I'm going to move it over a little bit. I've kind of shot myself in the foot. Let's put that over here. I is the square root of -1, right? So I squared would be the square root of -1 squared. Well, the square and square root cancel here, right? And so this turns into -1. And so this is really important that we understand that -1, that I squared equals -1. This is probably of the four that we're about to look at here, this is probably the most important, because it's going to be the most, well, this and just I by itself, right, is those are probably the two most important, because we're going to see in examples, we're going to see them used the most. So I cubed, let's talk about that one. So I cubed would be, now this is exponent rules, so this may be review. We're going to learn more, we're going to practice more about this and review it more in upcoming units. But we can split this up and turn this into I times I squared, because when we have like bases multiplied, you add the exponents. 1 plus 2 is 3, right? We're going to review that again later, but just that's what's going on here. So we just learned that I squared is -1. So this would equal I times -1. Well, what is I times -1? That would be -I. So I cubed equals -I. Right? So we're going to do one more, and then we're going to kind of talk about how this is a pattern and all of those things. So I to the fourth, what about I to the fourth? Well, I to the fourth, following that same rule, it would be I squared times I squared. That would be -1 times -1. -1 times -1 is 1. So I to the fourth is 1. Now, I'm not going to spend a whole lot of time on this, but it's actually cyclical. If we were to split this up, if we were to go to another one, I to the fifth would be I to the fourth times I. 1 times I is I. Well, we've gone back up here. I to the sixth would be I cubed times I cubed. So that would be negative I times negative I, which would be positive I squared. Positive I. Oh, look, we've gone to this one. I to the seventh would be the same as I cubed. I to the eighth would be I to the fourth. And this actually keeps on going. It repeats in a pattern a pattern of 4 all the way to infinity, right? And so when we're simplifying something with I in it, these are really the only possible ways it can get simplified. It can get simplified down to I or -1 or negative I or 1. Okay, so now that we have that, let's do some examples and kind of put some meat on this and see what a problem with an I would look like. Okay, so we're going to do a handful of different problems real quick. We're going to do several examples in this lesson. So let's start these. This is going to kind of combine two sorts of memory things, and it's going to combine simplifying imaginary numbers and simplifying radicals. So we've got the square root of 27. So first of all, we can turn this into the square root of -1 times 27, right? -1 times 27 is the same as 27. So, and then you may or may not remember that if I have the square root of A times B, then I can split that into the square root of A times the square root of B. Sorry, that didn't hardly fit on there, but that's what we can do. So we can split this into the square root of -1 times the square root of 27. Now, so you might think that the answer to this would be I times the square root of 27, but we can actually simplify it even further, right? So you may or may not remember how to simplify a radical. So we can simplify a radical using this same property again, and we can try to find a perfect square that goes into 27. So what are the perfect squares, right? So perfect squares are 4, 9, 16, 25, 36, 4 times 4 is 4 times 6 times 6, 7 times 7, 49. 8 times 8, 64. 9 times 9, 81, etc. Right? Those are the perfect squares. And I kind of gave it away with my mumblings, but in case you don't remember how I even got these numbers, you're like, that's great. I see those numbers. Those are perfect squares. I love it. Great, wonderful. Where'd you get that? So where did I get that? Well, this is 2 times 2. This is 3 times 3. This is 4 times 4, 5 times 5, etc. So perfect squares are just that, where we take a number and we square it and we get those numbers, right? And so are there any perfect squares that go into 27? Well, yes, there are, because 9 goes into 27. I'm going to go ahead and turn this square root of -1 into an I. I'm going to move this to the right. That's just an arrow in case you're concerned and confused. So this would turn into I times the square root of 9 times the square root of 3. Because 9 times 3 is 27. 9 is a perfect square. And so now this can turn into, the square root of 9 is, of course, 3. So this turns into 3I times the square root of 3. Wow. So that is now simplified. So let's take a look at this one. Now, for this number 216 is a bit more scary, right? This negative, we can turn this into, let me change colors, that way it's easier to see what we're doing. We can turn this into I times the square root of 216, right? Now the negative is taken care of. We just need to see if we can simplify 216 even further. So is there a perfect square that goes into 216? So we've got all these options. It's harder to do this in our head. So let's pull out our calculator. Let's do it. Handy dandy. There it is. Okay, so 216. Let's try 64. Why not? It might work. Divided by 64. Enter. It didn't work. Now, what I mean is we didn't get a whole number answer, right? And so if it works, you'll get a whole number answer because it divides evenly. All those words kind of mean the same thing. So 49 probably doesn't work. Let's try 36. So 216 divided by 36. Look, that worked. 36 and 6. Okay, so we can turn this into I times the square root of 36 times the square root of 6. Now, are there any perfect squares that go inside of 6? No, because neither 3 nor 2 are perfect squares. Now, I should note here that if I'm not greatly mistaken, let me double check. 216 divided by 4 also comes out evenly. Okay, so we could do something smaller, but then we would have to simplify it even further with the 54 because 54 is also, let's see, divided by I don't even know. I have to figure that. I have to think through that in a second. Divided by 4 again. No. 54 divided by 16. No. 54 divided by 6 is 9, which is what I really meant, right? So you could divide this by 4 and then divide it by 9, and you would end up getting the same answer ultimately. Is what I'm saying. What I'm saying is you can do it in more than one step, basically. But we discovered that it's simpler to just go 216 divided by 36. 36 is a perfect square. 36 square root of 36 is 6, so this simplifies to 6i times the square root of 6. All right, this one's a little bit different. This one we're gonna go ahead and do this multiplication, right? So -5 times 3 is -15. I times I is I squared. What does I squared equal? Look back at a page in your notes. I squared equals -1, so this will turn into -15 times -1, which is 15. That one's nice, isn't it? This one is a little bit trickier, a little bit scarier. So we're going to use this property again, but backwards, right? So this one, we're going to turn this into the square root. I'm going to write it all the way out. You could probably kind of skip a step or two here, but I'm going to write -6 times -15 here, right? -6 times -15 is positive, nice, 90. Are there any perfect squares that go in? I don't know why I'm just like growing this bigger and bigger. It's happening. I don't know. Are there any perfect squares that go into 90? Yes, of course there are. 9 goes into 90. 90. So let's turn this into the square root of 9 times the square root of 10. Are there any perfect squares that go into 10? 9 doesn't, 4 doesn't, nothing doesn't, I don't know, something. Square root of 9 is 3, so this will turn into 3 times the square root of 10. So those are kind of fun. Let's do another type of thing that we might do with i's and such. All right, so this one we're going to solve. Now, I'm going to make a note that you could solve this kind of by factoring, but we're going to solve this using the square root property. Okay, so we're going to solve for x first. So we're going to subtract 64 from both sides, -64. And so this would turn into x squared equals -64. I said solve for x first. I meant solve for x squared first, right? So now this equals that. So we can take the square root of both sides. We got to remember in our last one that if we take the square root of both sides, we're going to get a plus or minus. Es muy importante, right? Now, so we're taking the square root of negative, so it's going to have an I in it. The square root of 64 has a real deal answer. So this turns into x equals plus or minus, because we took the square root of both sides, 8i. Now you notice, and I'm gonna get a little more specificity on this, I think on the next one, if not the next, then the next x. But you notice that just like a variable, we're gonna put the number first and then the I. We kind of, in a lot of situations, we treat I like it's just any other variable. The only real difference is that if we get I squared or I to the fourth or something, then it cancels and turns into -1 or 1 respectively, right? So That's the only real difference. Other than that, we kind of treat it just like a variable. So let's do another thing. Yeah, complex numbers. So complex numbers, this is kind of the formal way to write a complex number. It has a real part and it has an imaginary part. Now, the A and the B are both real numbers. Each one of these is a real number. This and that are real numbers, right? This, of course, is an imaginary number. Imaginary number. Now, you notice, like I just said, that we have on this thing, we have the real part and we have the imaginary part. And when we write a complex number, we always put the real part and then the imaginary part. They always look this way. You might not always have both. You always at least have to have this part, right? Or else it's not it's not a complex number. It's a real number, right? So you always have to have at least this one, but you may or may not have a real part. Like you could have, like that last example where we had 8i. It didn't have a real part. It only had a imaginary part. Right? Let's do a handful more examples with some complex numbers. So this is another type of example we might see. We're going to find the values of x and y that make 3x minus 5 plus y minus 3i equals 7 plus 6i true. So you might be looking at this and say, wait a minute, I've got an x and I've got a y, I've got two variables. This is going to be a system. I don't like this. We're out of that. Well, it's not really a system. Not really, right? Because, see, what we have here is we have the real part. See how this real part relates to this real part? And then we have the imaginary part, which relates to this imaginary part. And so those two go together. So we can kind of set up two little baby equations and figure out x and y. Let me show you what those two baby equations are going to be. The first one would be 3x minus 5 equals 7. See, that's the real part. See, it's in the place of the real part. And then the other one would be this imaginary part. And it would be y minus 3 equals 6. Easy peasy lemon squeezy, right? So we're going to add 5. That cancels, turning this into 3x equals 12. My head is still fuzzy, just like it was on a video or two ago. I'm still kind of feeling a little bit under the weather. Sorry. It'll be okay. Divide by 3. This is going to turn into x equals 4. Look at that. Part of the answer already found. This one, of course, is even easier. We're just going to add 3. Plus 3, plus 3. This turns into y equals 9. 9. There we go. All right, let's look at a couple more. All right, this is even easier in a lot of ways. So we're just adding two complex numbers together. So to add two complex numbers or even subtracting them, basically all we do, and this goes back to what I was saying just a minute ago, all we really do is we pretend like I is an X or a Y or any other letter, and we just do the math. Since there's a plus in between them, we can just drop those parentheses because this plus isn't really changing anything. This one, of course, will distribute, spoiler alert. But this one, we can just drop those parentheses and turn it into 5 minus 7i plus 2 plus 4i. And then just like if this was an x or y or any other kind of variable, we find our like terms. So right here is alike with this one, and this one is alike with that one. So 5 plus 2 is 7. Negative 7i plus 4i is negative 3i, and it's that simple. No big deal. We've been doing that since like pre-algebra, right? No big deal. Now this guy is pretty much just as easy. We got to distribute that negative before we do anything else. That's very important. If you're going to make a mistake on a problem like this, this is where that mistake is going to happen, right here. Okay, so we got to make sure that you distribute that negative and don't just put it on the first one. That's an easy place to make a mistake. This first one, we're just going to turn it into 4 minus 8i. And then negative 3 plus 6i, because that just distributing that negative just flips those signs. Easy peasy, right? So then, just like up here, we're going to find our like terms, this one, and then these two right there. 4 plus negative 3 is positive 1. Negative 8i plus 6i is negative 2i. There it is. All right, we got 2 more examples of a different type and all those things, and then we're going to be through. Okay, so this guy, this one, the instructions, I forgot to write them on here. The instructions for both of these would be simplify, right? Simplify. So you might look at that and think, well, it's as simple as it gets. We can't cancel this because, we can't like reduce that or something because of this plus. That we can't really get to it. So what do you mean simplify? It looks like it's simplify. Well, here's the deal. Here's the thing. We don't want radicals. What's a radical? Radical is this thing, right? We don't want radicals in the denominator. You're like, well, there's not any, but there is. Because what does I equal? I equals square root of negative 1. So we have radicals in the denominator, and we don't want that. So how do we make not radicals in the denominator? Well, we multiply the top and bottom by the conjugate. Conjugate. The conjugate is the denominator with this middle sign flipped. Okay, so the conjugate here. Now, the reason we can do this, and you may be thinking, why? How is this allowed? You can just randomly like multiply stuff. Well, you can multiply anything times 1 and it stays the same, right? So we can multiply something times 2 over 2 because that equals 1. So we can do that. So anything over itself, so as long as we multiply top and bottom, we're good because we're really just multiplying by 1. So that's why this is allowed. Some of you are like, I don't care, just tell me what to do. So we're going to flip that middle sign. Let's turn this into 3 minus 6i and 3 minus 6i. So it's the same as the denominator with that middle sign flipped. Okay, so that's what we're doing here, right? So on the top, now this is very important. This is an easy place to make a mistake. On the top, we've got to distribute or possibly even FOIL if this one is a full complex number on the top, right? So 2i times 3i is 6i. And then 2i times negative 6i is negative 12i squared. Now that light bulbs should be flashing or warning lights or something. You're correct. Now this denominator, we've got to FOIL it, right? We've got to do this one times this one and times that one and here and there, right? We got to make sure we do everything. Es muy importante, right? So 3 times 3 is 9. 3 times negative 6i is negative 18i. You're going to notice something awesome, and this is always going to happen, so you can actually kind of shortcut it later once you get the hang of what's happening. 6i times 3 is plus 18i. Look at those. Look at those. Look at it. Just look at it. So beautiful. 6i times negative 6i is negative 36i. So you notice on the bottom in the denominator when you do these, you can shortcut and just do the first and the last because the outside and the inside are always going to cancel. Always. Oh, I made a mistake, didn't I? Look at that. What did I do? What did I do wrong? So I was too excited. I was too excited about the canceling. I made a mistake. 6i times negative 6i is negative 36i squared. So you may already see what's going to happen. If you don't, that's okay. We're going to walk it out. Don't stress about it. I squared, what does that equal? Negative 1. So on the top, we're going to end up with 6i minus 12 times negative 1. And then in the denominator, we're going to have 9 minus 36 times negative 1. You might be like, that cancels. No, it doesn't. Don't make that mistake. Don't do it. Doesn't cancel because of the plus and minus here. We can't get at that unless somehow we turn it into multiplication or something, right? So let's simplify on down a little bit further. So this is going to turn into 6i plus 12 on the top. And then in the denominator, it's going to be 9 minus negative 36. You could probably, yeah, you know what I'm thinking. I know you do. We got to ka-chink those. So on the top, this turns into, we got to put that real part first. So 12 plus 6i. And then over 9 plus 36 is 45. 45. Can we do any more simplifying? Yes, we can, actually. We need to turn this into a plus bi form, so complex number form. Also, what goes into all three of these numbers? 3 goes into all three of these numbers. What's 12 divided by 3? 4. What's 45 divided by 3? 15. What's 6 divided by 3? 2. So what did I do there, right? I divided everything by 3, and that's how I got 4, 15, and 2. And then I also just split it. Instead of this compound fraction, I just split it into 2. It's a little uglier, but with complex numbers, this is what we actually want right here. All right, let's do this one. This one's actually, even though it's the next one, it's actually a little easier because this time on the bottom, we don't have any real parts. So you don't even really have to multiply. You don't really multiply by the conjugate. You can just multiply by I over I. Now, why can we do that? You could multiply by negative I over negative I. You could do that. That'd be fine. Wouldn't hurt it. But you would get the same answer, but signs all flipped. And if the signs are all flipped, it's fine, right? But on the denominator, we got I times I, which is -1. Man. On the top, we got to distribute. Don't forget to distribute. Very important. So we've got 4i plus I squared plus -1. Let's write it all the way out. Plus I squared. In the denominator, we've got 5i squared. So that turns into 4i plus -1 over 5 times -1. So then we've got -1 plus 4i over -5. Now we need to split it, right? So we're going to split it up into the a part, the real and the imaginary parts and all of those things. So we're going to split it into, we got a negative over negative on this one, so it's going to turn into positive 1/5 minus, because we got a positive over a negative, 4/5 I. And that's it for complex numbers. We shall see you in the next one. This was a little longer. It's fine. You've had some really short ones. You'll be okay, I promise. There were several little things in this lesson. I'll see you in the next one. Hope you're having a great day. At this point in the year when I'm recording this and when we're doing it and whatever else, we're just nearly at Thanksgiving. So happy Thanksgiving, happy Christmas, happy Christmas, Hanukkah, Kwanzaa, all the things. I'll see y'all later. Bye-bye.